Unit 2.4 brought to you by Lego Ghostbuster Lady with her pack from the newest movie, I think. Not the most newest, but the all-female lead cast one. Anyways, 2.4, we're going to look at how to use technology to decide if two data sets are linearly related. Just a reminder, what we're looking for is constant addition for a data set to be linear, but we need to kind of further this a little bit. Constant addition for a set change in x. So in the unit 1, it was always steps of 1, but if it was steps of 10, we want to be adding the same amount every 10 steps. We call this thing, of course, the slope or rate of change, which we use the letter m, and of course we calculate it as y2 minus y1 over x2 minus x1. This, when you simplify this, we always make the denominator 1 and often write this as a decimal. So we're always looking at the amount we would add for one step if it's linear. I will show you how to do this in spreadsheets. I'm not going to show you a calculator because we've got Desmos, which I guess is a calculator, but it's an online calculator. And then we're going to look at how this technology creates these lines of best fit. And then we're going to learn what the correlation coefficient is. It's R, and what it tells us about the line. So the first thing I want to make sure we understand here is that what we're about to do is to correlate two variables. So we're going to be looking at, say, an x variable and a y variable. That's what we call them. In the math world, typically, you could use any letter you want, but the standard is x and y. As you look at in 2.3, that's how we create this two-dimensional graph. So when we correlate things, we think there's some sort of relationship between them, and that change in the x variable might affect changes in the y variable in some particular way. Like our author says, there are many quantities that seem like they might be related, but we don't necessarily know how without a really careful study. And it needs to be a design study where we control all the outcomes. Otherwise, there's things called lurking variables or other things that might actually be causing the change and not the two we're looking for. So here's a couple of things that we wonder if they're related. The dollar spent by a political candidate and the number of votes he, or come on, this is the 21st century, or she gets. Why do we even need to genderize it? The vote they get. Let's say that. Is there correlation? Unfortunately, yes. I think we could show a graph that looked maybe something like this, that the more money, if we made that the x-axis, the more votes that particular person gets. We should be clear, hopefully, I mean, it'd be illegal to give money to get votes, but we're thinking here ad spending, name recognition, all of that. Maybe the more likely you are to get a vote if someone knows who you are and what you're about, and that, of course, costs money. How about the adult test subject's height and their IQ? Is there any relationship between those two? And I would think there shouldn't be when we graphed it. I doubt that there would be any correlation. That maybe a taller person has a higher IQ or a lower IQ. Either way, these points should kind of be all over the place. And then a person's height and their shoe size, there should probably be kind of a pretty close correlation. It seems if your body is proportionally developed, that the taller you are, the larger your feet would be to help with balance. But again, that may not necessarily be true. And then the age of a car and its resale value. Yeah, presumably for your standard car, the older the car gets, the less it's worth. Of course, there's always exceptions to this. Here we're going to put resale value on the x-axis. Wrong again. We're going to put age on the x-axis and resale value on the y-axis. We could have a point here where it's a very new car, but maybe it had flood damage, and so it's practically worthless. And we could have an old car that's like a collector car that has been carefully preserved and it's worth more than it originally was. So the age does not cause the resale value, but there's certainly connections, a correlation between the two. So what we're about to do is create scatter plots and look at what kind of pattern do we see, and is there a linear correlation or an exponential correlation? That's what we're headed towards. So here's a data set. These are some fast food sandwiches, hamburger, cheeseburger, quarter pounder, at different fast food restaurants, and we got grams of fat contained in the burger and the number of calories. And we're suspecting that there's a correlation between the number of grams of fat in a burger and the number of calories in that same burger. So we're to hand plot these, and it's actually not too terrible. When I first looked at this, I'm like, oh, I don't want to do this, but I'll do a few. So for this 9, we're noting that these are all steps of 1 here. So here's our 9, and we're looking for 260. And if you count how many steps there are between the 300 and the 400, we've got 1, 2, 3, 4, 5. So we're taking 100 units and dividing it by 5. So each one of these represents 20 units. So this would be 220, 240, 260, 280, 300. So 260 was right here. We could plot that point. There it is. I'll write that out as 9, 260. You can see this is really tedious because now we're going to do 13. So 10, 11, 12, 13. Here's the 13. And then 320 would be one line above the 300 line. And that would be 13, 320. I'm going to stop here and say, in my opinion, there is no need to graph things by hand because we have these powerful tools called Desmos. So let's put this table into Desmos. So I'm just typing in 9 as our first point and 260 as the second point. And then 13 and 320. Okay, so I've got my data values in there, and I can't see anything, right? I'm looking at this, and there's nothing on the graph. Well, this little button, the Zoom Fit button, is a perfect way to get a nice picture of the data set. Once you hit that, then you could zoom in a little bit if you wanted to. And this appears to be the exact same view that we have on our paper. So I'm just going to kind of quickly copy that onto here. It was like, and so there's another mess. Let's call that the same graph. So our goal then is to find a line that more or less passes through all these points as best as possible. Now, our author here says use a straight edge and draw a line through here. I'm just going to, that looks like a nice line that goes through it. All right. So he's got a good point here. Note that it's possible that the line that fits the data best doesn't go through any of the points itself. The goal here is to get a line that has the most of the points clustered as close to it as possible. And we're not going to do a whole lot of this. I'm going to talk you through a little bit, but we're mostly going to use technology to do the rest of this work.